let's kick off. Yeah, it's 7 o'clock. So hi everybody, welcome to the fourth session of the Global Technical Inserto Reading Club. This month we're going through chapters 8 and 9, and we've got Marcos and Fergal who are going to read us through chapters 8 and chapters 9 respectively. And I'm going to do a little piece at the end on second half of chapter 9 and those kind of appendices B, C, and D. Yeah, so Marcos is the co-author of a book, The Brazilian Derivatives and Securities, and Marcos is also a PhD candidate at the École Polytechnique. He's been working in finance for more than 25 years, mainly in Brazil, including risk management and trading. Fergal McGovern is a quantitative developer at Energy, focused on the UK power market. And my name is James Sharp. I'm an actuary based in the UK, working on kind of capital requirements and reserving for some UK and international insurance companies. So a bit of background on the reading club. So it's a group of us interested in learning more about Nassim Taleb's risk, statistical, and finance work in the technical inserto. The aim is to read through the first volume in 2021 and beyond. The book itself is available freely at this link here, so there's a PDF you can download by clicking there. I got a copy from the book depository, but yeah, it's also on other bookstores you can find online. The benefit of reading in a large group, you're getting a lot of different views, discussion, making code available, and so on. It's really helped me, I know, to get to grips with some of the concepts. We'd like to thank Jake Billing for putting the recordings and background information on this website. So we have a website here. There's a GitHub repository containing all discussions and code and so forth. And thanks to all the contributors to date, and also to the network of consulting actuaries for the Zoom link. So with that, if I can hand over to Marcos to take us through through chapter 8.
Okay, let me just try to share the screen. I don't think it's. Can you help?
Should now be possible. I think I've just set it to everybody. Okay. Or do I need to unshare somehow?
Okay.
Okay, perfect.
Mm-hmm. Okay, so let's discuss chapter 8, and chapter 8 is one of my favorites. I think that just hold on a second. So sorry. So chapter 8 is one of my favorites, and it's based on the how much data do you need paper. So what we are going to discuss is we'll discuss a bit about fat tails, and then we're going to discuss some of the distributions we'll be looking at. Then we'll discuss the concept of mean absolute deviation, then look at kappa, the metric introduced in the chapter, then some of the stuff that we need to do to continue the study, and some conclusions. So if we were to summarize at least my view on this chapter and what the book was about up to now, well, if we have fat tails, extrapolation is dangerous. One of the conclusions of this chapter is that under fat tails, diversification becomes harder. Mainly if you have seen Nassim's presentations on his YouTube channel, he discussed how when you have one normal random variable and then another, and one could be positive and one could be negative, and they compensate each other. So when you have fat tails, all this compensation between the positive and negative possible values, gets drawn out by the risk of the large variations. So this is something that we need to look at. And we also are going to look at the term structure of the likelihood of kappa is perhaps what we need. So Nassim can jump in at any time if I'm making any mistakes, which I probably am, but let's wait and see. So first we start with the repetition of one of the figures of chapter 5. So we're looking at different presentations under a log-log plot and looking at the probability of the variable exceeding a particular value. And we can see that the brown curve here, it's standard Gaussian. And we see here the log normal with the low volatility, and we can see that if we increase the volatility, probability here becomes almost flat in terms of log terms. So just changing the volatility of the Gaussian is a kind of
Marcus, I'm not sure we're going through your slide. I can just see the first slide, contents page, is it?
Okay, let me try to stop share and resume the share.
Oh, there we go. Perfect. Yeah.
Okay.
Nice.
So here, okay, back to the brown curve is the standard Gaussian. The red curve is the Gaussian with a much higher volatility. So we can see how the log normal changes behavior with the low volatility and the high volatility. And we can see the cubic student, and we can see a Pareto here. So another way of looking into these probability distributions is, can you see the chart now?
Yep.
Okay, so if you look at surprise, and if we define surprise as minus log of the probability, so we can see that when something happens here, if we have the standard Gaussian or the low volatility log normal, if something happens around here, we're really, really surprising. So changing the volatility of the Gaussian, so we say, oh no, we are less surprised by something happens, doesn't help a lot because this is not really flat. So when we look at possible fat tail distributions, so we can see the log normal with the high volatility or student, cubic student or Pareto, we see that kind of flat curve. That helps us to model something and say that we have fat tails, and this will help us later. But all these three different curves have different behaviors, and this is why we need some other metric rather than just looking at the surprise. So if it's surprisingly not easy to find available good formulas online for the mean absolute deviation, if you look at the method page, there are wrong formulas there. So there is even a Stack Overflow page discussing the mistakes in the method page about the mean absolute deviation. So we can look, we can get some help with Mathematica and do the expectation calculation using Mathematica. So for the Gaussian it's simple. So it's square root of 2 over pi times n, and that's square root multiplied sigma. For the student t, we have n equals 1. It means that I'm just looking at one single realization of a student t distribution. We have this formula. If you look at n equals 2, Mathematica will spit out a nasty result full of functions that are that blow up, but the first term is
sorry, it's not a single realization. I guess it's a single summon.
Yes, a single summon. Sorry.
Okay. All right. Okay.
Okay. So if you look at two summons, that formula. So if you just substitute the for here by 2, this is part of the formula that Mathematica spits out when you do the expectation. But when we test it and found that with the for here we get the good results for 2 summons. But if we try for more than 2 summons, no luck here, no luck there. So going over the other distributions for the log normal and the Pareto, we have formulas for only 1 summoned. And what we're going to do to look at the other results. So we can calculate here. So this is for the Gaussian, the blue curve is for the Gaussian. Sorry. Yes.
Mark, can I barge in just to give some background to people, say they sure. Just tell them what we're trying to do here? Okay.
Yes. Okay.
So I'm measuring, say I have, it's very simple. If I have one summon, it means in one observation, I have the distribution is like that. Okay, this is n equal 1, all right? And the point is if I have n equal cap n, some large number, so it's going to be smaller, okay? So we take the mean deviation, the expectation of the mean deviation, you see, of absolute of x, okay? Or here x plus x, two random variables, you see, x plus x1 plus x2, you see, or x3. So this is the n, and what happens to the behavior as n becomes larger. That's pretty much what we're trying to do here. So the idea is that under fat tail, this distribution doesn't compress when you take the average. You see?
Yeah.
Here he's working with the sum, how the sum increases. And the way the sum increases is visibly the mean deviation of the sum. And we're using mean deviation because standard deviation doesn't work for things that don't have a standard deviation, okay? If it's Cauchy, you see, it increases like that. You see, you're expected whatever dispersion, assuming it exists, conversion to Cauchy, you see, it's going to be linear. And for a Gaussian, it's going to be root n. And we're looking at things in between. And that's pretty much what he's showing here in this graph.
Yes.
So clear enough? So I was, so I can.
Yes. Yes. Okay, so we can see that.
I just gave the intuition of what we're trying to discuss.
Of course. Of course. Yes. Yes. I'm
sorry.
I've jumped over some details, but
and also show off. I have a board. I have a board here.
Yeah. So yeah. So we can see that when we look at the log normal, and so we can look when we look at the log normal, we will go from this that looks much more like the Gaussian. When we increase the volatility of the log normal, it becomes much closer to linear. So if it's linear, it means that the large deviations are never always taking over the risk. So I'm not as good as a mathematician to go there on the appendix and do all the symbolic calculations. So what I typically do is run Monte Carlo simulations a lot and a lot and a lot. So what I did for the student T here is that we know that if alpha goes to infinity, student T should be a Gaussian, and the Gaussian becomes grows with the square root of n. So we are going to feed for each value of alpha, we are going to feed n raised to gamma to this curve, and we know that gamma should be between 0.5 and 1. So for example, if we use for the cubic student T, If we have gamma equal to 0.56, we have this blue curve here. And if we simulate with of 1 million runs, we get this result. And we do the same fit for different values of alpha. And we have something that we should expect something that for large values of alpha is 0.5. We should expect that as we approach 1, as alpha approaches 1, we should have a value that is closer to 1. So an interesting fit should have this form of 0.5 plus 2 raised to something closer to -1. So this is a good enough fit for us to understand that, yes, if we use that approximation, we should have a good enough model to look at different values of the student T instead of just looking at one specific value of alpha. So it's an useful approximation. So when we look at the carefully deduced formulas on the appendix, so for the cubic student T, we have Nassim's formula, and nice. If we go and simulate it to n, if we go and simulate kappa 1 to n and compare with the formula, we have a perfect match, which is excellent. If you look at the other formula in the appendix for the log normal, for sigma equals 0.5, we have a pretty good fit here, but some bias here at the beginning. And when we look at the formula for sigma equals 2, I found some difference here. So I'm not sure what I did go wrong, but there is something that is worth looking at. I know that the deduction of the formula had some particular hypothesis that I'm not sure whether the sigma equals 2 falls within the hypothesis used for the deduction. So this is something that the code that I used is going to be available at the GitHub page. So this is something that everyone can go and explore and check.
So your simulation is below the formula, but it has the same shape anyway.
Yes.
So it's a scaling difference. It doesn't matter. Okay.
Yeah. Yes. So you see that for sigma equals 0.5, it's really close. It seems a bit off at the first values here. But
the other one is sigma equals how much in the other one?
So this one is 0.5 and the other one is sigma equals 2. From 2...
Yeah, okay, with sigma equals 2 for a log normal, you have a huge sampling error.
Yeah. So I try with something like, if I'm not mistaken, it's either 500,000 or 5 million runs. So this is something that is on the to-do to check whether this...
Okay, it could be the formula is wrong, but I doubt the formula can be wrong because it's analytical on one and not the other.
Yeah. So this is why I quoted Gru the Wanderer here. So I probably there's something that
the formula would work on low sigmas and not on higher sigmas. But anyway, the formula is an approximation. No, it's not an equality. Is it equality?
The formula
is an approximation.
Yeah. So okay, so this is something that we can check to see whether we can improve the approximation. Okay, so one interesting thing that we are looking at kappa, but as Nassim always points out, it's not enough to have, let's say, point estimates. So what is the distribution of kappa? So I run the process to find kappa with, let's say, 5,000 runs. Then I run that 5,000 times. So if I run the student T simulations with 3 different values of alpha, and I run each, and I run 5,000 simulations of the student T to find kappa, and then I run this process 5,000 times. This is the dispersion of the values of kappa that I find. So we can see that even for alpha equals 10, I have a chance to find the negative values of kappa 1, 2. And so even finding something that if I measure something and then I have a kappa of 0.2, well, it doesn't mean that my alpha is 5. It means that more likely than not, my alpha is 5, but there is a small chance that the alpha is 3 or a small chance that alpha is 10. So one particular realization cannot tell me exactly what the underlying distribution is. So even if we compare two different, so if you look at the table 3 on the paper, so we choose a student T that has the same kappa as a Pareto, so we find that student T alpha 2 and Pareto alpha 3, and we find that they have kappa, expected value of kappa of 0.45, something close to that. And we see that they start with the same kind of distribution, but they behave differently over time. So this is an example of the term structure of kappa when you look at the uncertainty. So imagine that you have this histogram for different values of n. So I have this histogram for kappa 1, 2, and then I have this histogram for kappa 1, 12, kappa 1, 32, and so on. So for the cubic student T, so we start here, but with a large dispersion, but the dispersion really decreases quite fast over time. For the student with alpha 2, so we start at 0.45 something, but that dispersion decreases quickly, and we fall in after 122, we are close to 0.35 or 36. A Pareto starts at the same place, 0.4 something, but decreases faster. We are going to see why on the next slide, but it's still, if you look at the uncertainty, is larger on the Pareto than on the student T. So the Pareto is still more volatile. So, and we can see why, because you're looking at a Pareto tree here. So even after 100, kappa 100, we are falling from 0.30 something to 0.2 here. So we are falling quite fast. But the student 2 is here. So even here, the relative decrease is smaller than here.
Marcos, we had a question there from
yes.
Kartik Menon. So I think it comes back to those 3D plots you had on the previous slide.
Yes.
It was just asking why do the term structures have local minima and maxima? Is that simulation?
No, this is a simulation. So this is a simulation. So we see that in here, for really small values, it's quite spread out. So we see here for example, for the alpha 2 here, we see that we had simulations with values close to 0.8, and we had values close to 0.1. So it's really spread out at the beginning, but when you go to 20 and then 50 summons, then that uncertainty decreases. So you kind of converge to
tighter point.
yes, so you converge to a much narrower band for the value of kappa.
Are there a couple of peaks though in red there? It looked like it kind of went up.
Ah, yes, these peaks are these peaks are here because it's really concentrated here, but it's only 5,000 by 5,000, so we're going to have some irregularities here. So this is kind of a mathematics is smoothing out the histogram, but we don't have enough data in the histogram to make it really a kind of nice analytical approximation here. It's just to have an idea of this, of the movement, not only of the convergence, but how the dispersion decrease, the rhythm in which the dispersion decreases. So we see that by 20 or 30, the dispersion has already decreased a lot. But after let's say 50, it takes a lot of time for that dispersion to decrease in the Pareto case. So what I try to cover here, it's really kind of looking at what the concepts and the formulas of chapter 8 were. And I think that is the way I usually do this is I try to code the simulations, and the notebook is going to be available on GitHub so everyone can investigate and check whether what I did was right or wrong, and investigate and do whatever they want with it. So what we have to do, I can improve the code for performance. So if I run in 50 million or so, I crash, the Mathematica crashes. So I was much more lazy in terms. I was lazy in terms of trying to do the analytical calculations. So I did not do any previous work before putting the formulas into Mathematica. So I think I had a much better job on the appendix than what I did to arrive at the formulas that I put for the MIDs. And
the objective of this is much less to have a precise formula than to understand how to rank things based on power laws. That's the objective. So that's not, it's not a big deal, you see?
Yeah.
Not having the right formula is not the formula is not the essence of it. And also this shows how the log normal can behave in a very weird way.
Yes. And so one of the things that will be interesting is to have a more formal definition or a better way to have an approximate formula for this kind of likelihood, because it's really, so if we are observing data, then if we are going to think about which kind of distribution am I at, imagine that I have all these kind of possible likelihoods, and then each of the possible distributions has some chance of being responsible for the data that I'm looking at. And if I have an approximate formula for these likelihoods, then I can start having some Bayesian-like inference of these possible models. So what is interesting here is also an appendix on, let's say, some of the people here work with financial data. And when we look at large deviations, we have a pretty interesting problem of truncated distributions. So there was a presentation 2 or 3 years ago about how we cannot observe larger variations on equity indices anymore, because after 87, and so in the mid-90s, regulators introduced circuit breakers. So you have limits for the largest daily variation on the index. So you won't find the S&P falling 37% in one single day, but you'll find a lot of 10%. So an interesting thing is, if I have, is one of the issues that on an earliest chapter, there is the kind of a figure one is, okay, there's a lot of data here, but then something here. So I said, no, this is not a problem. So it's likely that sometimes you'll find a lot of data on a particular large variation, let's say 10%, which is a typical value for a circuit breaker on an index. So if you see this large 10%, more likely than not, you are kind of, you should find a way to say, okay, infer what will be without the circuit breaker, you have probably some larger variations. So how do you deal with this kind of truncated distributions to infer the power loss? So this is a very interesting challenge. And so I think that, I'm not sure whether Nassim remembers or not, but there was, I think that last year perhaps, there is an AKR paper about puts and large deviations and so. Some strategies that worked in the past might not work because of that. So if you're looking to, let's say, buy puts or buy the wings on financial securities, it's worth looking at which securities are not, let's say, monitored by regulators. On which securities I'm able to observe and interact with really large unbounded prices. So if you look at single equities or Bitcoin or something like that, then you are able to find still those large deviations. So if you look at GameStop or AMC or whatever, you'll see 100% intraday moves. But if you try to look for large moves in the index, it's perhaps almost impossible to find them because there is this large regulatory action into it.
It is actually, I mean, I don't understand this point, because we should not conflate lower volatility and thinner tails.
No, I'm saying
that GameStop has a high volatility, Bitcoin has high volatility. Doesn't mean they have fatter tails. It's another matter.
No, but I'm saying that if you look for, let's say, for this kind of really large moves, it's easier to find really large moves in single stocks or in unregulated stuff.
Yeah, this idea of truncation is another matter. I mean, I can understand, but this is not the context for. You see, this is a technical thing on distributions.
Okay.
All right.
It was just an appendix.
We can have a discussion, another one on truncation. Let's not conflate. You see.
Okay, no problem. But just
this is then you're saying it's no longer that distribution. Then it's a different discussion. You see my point?
Yeah. Yes. Just that was an interesting reminder. So what is left to do?
Karthik is asking, why does the term structure have the local minima and maxima? It's entirely sampling error, because you're doing interpolation with too many degrees of freedom. By the way, Karthik is a person who can solve problems on the web faster than you put them in.
Oh.
That's right, Karthik, I guess, no?
Yeah. So what is left then is to extend this framework to multivariate distributions and include not only correlations, but autocorrelations, thinking about, because the one thing that I really enjoyed on the chapter is when we look at, when you look at not only the summons as realizations over time, but as summons as realizations over securities. So when I think about correlations, I think about the correlations between securities, and when I think about autocorrelations, I think about the correlations of those realizations over time. So one thing that we can do with at least if not analytically, then we can try to do it at least numerically to see what could happen. So the idea is not to go over all the formulas, but okay, this is what we find when we run the calculations that are described in the chapter. So, but that's the idea. And one of the lessons that I had is with most data shouldn't allow us to be overconfident in trying to estimate the second decimal place of parameters if we are not even sure about which distribution we should be attributing to this data. And what I really like is the approach that, okay, we understand, okay, what are the properties of the model. So kappa is an idea of qualitative measure that one single number can describe, let's say, the behavior of the speed of decay, and also the term structure of kappa can describe the speed of decay and also the degree of fat tailwinds. So it was really well taught, and this is why I thought that this was one of my favorite chapters, and I said this is why I wanted to present it, so to see whether more people would find it interesting as well. So thank you.
Okay, yeah, nice one. Thanks a lot, Marcos. That was really excellent. Thank you. If people have questions,
stop. Yes, so I'll stop sharing the screen and
yeah. Go for it. If anybody has a question, please dive in. But I had one there, just like more simple question on the kappa, or maybe two. And one was, in principle, this is a way of comparing tail fatness for different distributions. The kappa is, so you just kind of calculate it, and then you can compare like a log normal with a Pareto or student t with a, and so that's the main purpose of this. Yeah. Okay.
May I?
Yeah.
Yep. Okay, may I comment? Okay, the whole thing is the problem of comparing distributions, that there are different bases. Let me give some intuitions. People are used, I mean, if you read Mandelbrot's work, of taking the stable distribution where you have that parameter alpha, the alpha stable distribution, which is, you know, if alpha is non-finite variance or say Gaussian, and if it's in a Gaussian domain, treat it as Gaussian. The problem is if you're doing statistical inference, you don't reach that limiting distribution immediately. You reach it very, 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 very slowly. The log normal may, under summation, reach the limiting distribution, which is Gaussian, but after really infinite. Okay, we don't have enough time, you know, left on this, you know, planet for that. Okay, so the idea is to be able to compare, to say what is fatter tail, a log normal with a sigma of 1 or a Pareto distribution with a alpha 3. And given that you're normalizing by the mean deviation, any distribution that has finite mean deviation can be compared to one another in terms of how much data do I need. That's simple. And now this doesn't come so much from finance or adding things. It comes from straight statistics, where people tell you, well, I have 30 points of data, I have significance. And here you can tell them no, because under this distribution, significance will require a different one, and kappa allows us to do that, to do the translation mechanism. So that's why I was saying as a metric to compare fat tailness across distributions. There's no other tool that is available for us to compare, because once you go from a class of Gaussian to non-Gaussian, in Gaussian you have kurtosis. You see, in a Gaussian domain, you have a kurtosis. A non-Gaussian and finite variance domain, finite all moments domain, you have a kurtosis. So you can say, okay, this distribution has higher kurtosis than the Gaussian, all right, by that much. It's fine, we can compare, but you cannot jump distribution classes because a Pareto doesn't have a kurtosis. Hence that idea of the kappa, of the speed of, you know, tracking a certain a certain sample size.
And one interesting thing also is when you look at the charts of the different and how the mean deviation changes, it goes. I mean, people will use it to see on VAR. Oh, square root of time rule to expand it. We know that the chances of this being correct are null because nothing is Gaussian. So risk. So if you are looking at risk over time, one needs to, let's say, get rid of this idea of, oh, square root of time works. It shouldn't work. I mean, we know that that we won't find Gaussian things here.
Okay, great. Okay, so we had another question there. Not sure quite. So what does Nassim think about the p-value having a great power to determine if something works or not when it's 0.05?
Yeah, is this question for me or for?
It is. It's addressed to you. Yeah.
It's unrelated to the chapter. I think there's a chapter on p-values. That kind of the 19 chapter 19, whatever, I forgot the numbers. So I can quickly give the answer that p-value makes no sense if there's no hacking. Okay, if it's above 1%, and if there's any hacking, it makes no sense unless you have something even smaller than 1%, because all you have to do is 2-3 times, because it's a distribution that has most of realization way below the mean. So if your p-value says 11 or 12%, the true one, 50% would be below 0.05. So it's very easy to get a spurious p-value. Sorry?
With that, we come on to that in a later chapter anyway, though, it sounds like.
Yeah, that will come back. It's more technical, probably one of the most technical ones, where because people don't realize that p-value is a random number rather than it's just a metric. You see, it is a random number. I mean, practically every metric is a random number. Like if I measure you, I'm not going to get exactly the same measurement every time, particularly if I drink, okay, or if you drink, or if you move or something. So you always have measurement error, but for some measurement error is substantial.
Yeah. Okay. Okay. Great. All right. So, are there any more questions? Please just put on the Q&A or the chat. But otherwise, we'll hand over to Fergal for start of chapter 9.
All right. Thanks, James.
Thanks, Marcos. For I'm very honored that Marcos was a friend of mine for a long time, and as usual, I promised to heckle him, which I will now do with Fergal.
All right. Can you see the screen okay?
Yep.
Yeah. Chapter 9. I'm just doing the start. James will follow up. This is about extreme value theory, something James and Ron are familiar with as actuaries. It also overlaps with our very first introductory session. So in the introduction, we're start off by talking about the distribution of the maximum. So if you take samples and in each of your samples, you calculate the maximum, what is the distribution of your maximum samples? So one of the things is that there's the hidden part. So if you're looking at like the highest water level in history, the past maximum is not always a good predictor of the future maximum, just because, well, it wasn't a good predictor of the last maximum, because you would have been looking at a max that was lower than that at the time. So then one of the interesting things here, it develops the theory, and it shows how when you're working with power laws, which is relevant for anything in finance or economic data, you can sort of see a relationship between the power law and the distribution of your maximum. So maybe if you want to think about your largest loss in a week, and how that's distributed, something like that. And then there's further parts about the hidden tail and the distribution beyond a threshold, which James will look at. So what I'm going to focus on is all for the assumption it's Pareto random variable that's being sampled, and they're all independently distributed. Basically, if you want to understand the distribution of the max, you say, let's take a sample that's size n. So you've got n samples from a Pareto, and you're calculating the max. So then if you want the cumulative density, you're doing this thing where you want the probability that your max is below x, which is just the probability that all of the ones in your sample are below x, which is just the product of the individual CDF functions. So it's really just, if you know your CDF, the probability of your max being below x is just the CDF to the power of n. And knowing that, you can either do Monte Carlo and work out what you want, or in this case, for power laws, you can do it analytically and get some expressions. So moving down a bit, I'm going to skip to this theorem. So there's a theorem that says if things behave well and your maximum converges to a distribution, then that distribution is known as a generalized extreme value distribution. So it looks like this expression here, and part of the derivation involves taking the max, norming it with a location and scale, and if these exist, you can get the generalized extreme value distribution. And then it turns out that there's 3 different subtypes within the extreme value distribution. So it really depends on this shape parameter, which is closely related to what we know as the tail parameter in power law. So moving down, here's the 3 distributions: Gumbel, Frechet, and Weibel. So of particular interest for a power law, you have the Frechet, which I'm going to talk about. Briefly mentioning with the Weibel, there's a finite support. So I think that means there's an upper limit bounded maximum. And with Gumbel, this one is relevant for the normal distribution or similar. But we're going to focus on this one here. And I've got a notebook, which I'll show shortly, with some replication of this following plot. So yeah, what this plot shows you is how the tail of a power law gets you a Frechet distribution when you're looking at the sample maximum. So really what we're comparing is, on one hand, we've got the Frechet, which is an expression like this. And on the other hand, we have this nth power of the Pareto CDF. And in the book, you have, this plot is a ratio of sort of the exact distribution divided by the Frechet distribution that's fitted to it. And you see that it's not going to work well for small n, but I mean, we're looking at a maximum, so we're not really looking at small values, and it's fairly accurate when you get to a large enough n, and you get any larger, and the Frechet and the exact distribution match up together. So if you're trying to apply it, you could use something like this plot to eyeball where you think it's going to work well. So then there's a comment here that the PDF will give you a similar plot, and I've got a notebook which makes the PDF ratio, which I'll show just now. I think there's a question here about the symbol for the tail parameter. So I think it's like the Greek letter psi, KSI. And I guess it's called the shape parameter. You'll probably find more information with that term. And then it's related to the alpha. So if you look in the book, there's, for example, with Frechet, the shape parameter is 1 over alpha. So alpha is positive and your shape parameter will be positive in this case. And yeah, let's take a look at the notebook. So I'll just run it. So first, I just defined the PDF for the maximum of burrito samples. So if you do set your alpha, set your like minimum value, and then it's getting the PDF of X for when you've got n samples. So I took the formula from the book, which is down here, 9.3. I expressed that, and then I made the Frechet one as well. The Frechet one is a little bit more involved because whereas we saw there's an expression first up here, and it looks a little bit different from the expression that we have for the Frechet PDF down here. But Marcos helped me to understand where that comes from. So I'll try and share something like this afterwards. But if you use Wolfram and plug in the symbols, you can see the, move this, you can see the original expression. Then if you switch to PDF, you can see the PDF. And then if you plug in, instead of AN and BN, you plug in your beta and 1 and shift X. I think this is just for convenience to shift it. You can work through and get the expression with the beta term. So it sort of just works through depending on what you plug in. And you'll get that 9.4 expression. So I've got that in the notebook. And then I just do the ratio of those two PDFs. So Pareto divided by Frechet. So if they match up, you'll get a 1. And if they don't, it'll be away from 1. So in this case, I'm setting, oh yeah, I just do a few tests to check the functions work okay. That one's not happy. And now what I'll do is I'll look at different n. I think it's n. So I've made a table here. So depending on what value you want the probability of, so X, I've just taken integers all the way down to about 50 or something. If your sample is 1, so that's just a Pareto without really doing any maximum, it's just a Pareto. Now this is Pareto samples of 10 taking the max, Pareto samples of 1,000 taking the max, and you've got your probability of this value X. And then I do that for Frechet as well. So you've got a different table and we put them on top of each other to get the ratio. And so you get this ratio and you see at the beginning, especially for like the larger samples, it's not near 1, so they're not equivalent. But then if we go into the tail, it's near 1, which we'll see in the plot. So I'm just plotting that. I'll skip down and plot the table and then show the PDFs. So here's the table. It's really what we have in the book, just doing the PDF ratio. And I've added in, so we had those 2 lines for about 100 and 1,000. And once you get past the small values, the Frechet and the exact are equivalent. And then I just added in what happens with smaller samples of n. And just to visualize, I've got a plot here of the probability density. So it's a little bit hard to eyeball. They sort of look similar. That below is the Frechet, above is the exact. But if you look closely, they're not the same for the earlier values. But then, say that, let's look at the Pareto when you're taking the max from 1,000 samples, most of the values fall here above, say, 15. And if we look at the ratios above 15, it's pretty close. That Frechet and the actual distribution are quite similar. So that's playing around with a notebook I'll share afterwards. And I'll go back to the book now. Yeah, so this expression here is part of calibrating the exact to the Frechet distribution. You get the PDFs and you set them so that the limit equals 1. And you end up, that's how you figure out what beta should be in that expression. Properties here. So the tail exponent of the maximum is the same as that of the random variables themselves. So I have a question, maybe if Nassim might know. Does this mean that so is the Frechet distribution a power law in its tail? Or should I read it more like, how should I read that?
No, it is, a power law is mostly, for the tail.
Yeah.
Yeah, if you don't have a power law tail, you're not in a power law class. You see, it's not it starts at some point that I call the Karamata constant, and then beyond, or Karamata point. So the Frechet, the power law conserves under maximal selection of the maxima.
Yeah.
You see, the power law is conserved under addition, under a bunch of things, and the maximum of a power law distribution is itself a power law distribution.
So if I have like alpha of 2 in the power law, the Frechet will also have a tail of
alpha of 2. Yes, it conserves the alpha. From what we see from the asymptotically, if you take it, you see that it conserves the alpha.
And should I be, if I play around with the formula, should I be able to see the power law when I put x towards the limit in the Frechet?
I think so. It must be it must be. I think I've done the exercise there. Look at this. I've done the limit. Look, very large to function equate. Yeah. And then I took that ratio. They effectively do equate, except for some constants. So you have norming constants. I think I don't know what I've done there, but I think that you're taking the Frechet and then psi of x. Okay, it's for norming constant. No. I must look at it differently. The exercise should be very easy. If you take the limit of this thing, I can do that as you're talking. We can verify. Okay.
So
because you here look at here, you have x to the minus alpha. If you keep that page open, x to the minus alpha minus 1. Okay, that's the density. No.
Yeah. That's right.
Yeah. So when you take so it'll be minus alpha for the other one, and the exponential, this one would wane, and in front of it is a norming constant.
Okay.
You see, did I derive the Frechet here by organically by taking the maximum of a bunch of power law variables? Looks like it, because the L is a Pareto, scaling constant. So it looks like, yes, it must be. If it's otherwise, I will come and make amends.
Yeah, I'm a bit slow on the spot, but when I looked at it, I can see how this works, and I can see that if the ratio is 1, they're sort of the same thing. I was just trying to play around with this and get rid of the exponential so that I would have more of what looks like a power law survival.
No, this exponential that wanes, it's e to the minus x, no?
Okay, so x large, and then you can focus on the x part.
Exactly.
Okay.
Okay, so this one wanes, so that you have x to the minus alpha. That's a PDF. If you take
Yeah.
the CDF of the Fréchet, you should get to x to the minus alpha.
Yeah.
Sorry, I haven't read the chapter in 2 years. I'm not fully.
Yeah, sure. Maybe I'll quickly show. If we take, if you take the CDF, it's this one here.
Yes.
So I guess I'm not too familiar, but in my mind, a power law looks like like Lx to the minus alpha.
Yeah. Work the CDF and you get x to the minus alpha.
But okay, but putting
Let's look at the limit.
X.
Take the limit of that, since you have Mathematica open. Take the limit of this, okay, to
Yeah.
the minus x. Assume B1 and A1 equals 0, all right? E minus
Yeah.
x. Yeah, take the limit and look, it'll give you x to the minus alpha.
Okay, I can try it here. What I had is Python, so I might not be good on the spot with the Mathematica, unless Marcos wants to give it a shot.
Hold on, I have Mathematica open here.
Yeah.
E minus x minus 1 to the minus alpha. Yeah, there we go. So when you do log plot, Fréchet distribution.
Yeah.
Survival function, Fréchet distribution, to say alpha 2 comma 1 x from 1 to 100.
Yeah.
And you will see it.
Okay. So yeah, linear survival plot, basically.
Exactly.
To see.
So yeah. So it is a power law.
Okay. That sounds good. Thanks for that. I'll show as well the Gaussian case. It's really a repeat of this, but for the Gaussian. Oh, and then, yeah, the property 5. So what we just discussed, asymptotically, for as long as you're not looking at small values, the power law and the Fréchet will match up. So then you get the Gaussian case. It's similar to what we looked at before, but the limiting distribution is approached with extreme slowness. So basically it doesn't work as well. And you can see like the plot here, it's dipping, it's not just the nice flat at 1. And for the PDF, it's sort of worse. It goes up here, they're not matching up, the exact and the Gumbel approximation. And then if you are doing this, there's different ways to plug in your values if you want to use your Norman constants. So there's this here, or there's this referenced as well. But basically you should use the exact distribution. So here property 6 says that if you're working with the Gaussian, instead of trying to use the extreme value distribution, just work with the exact one. And by taking the CDF and doing it to the power of n to get your CDF of your max, you can get a better expression for working with. And that's where I'll stop and hand over to James. Unless there's any questions. I think you're on mute there.
Sorry.
Got it.
Thanks.
All right.
Yeah, I was just going to say, if there's any questions, please add to the chat or the Q&A as we're going. Otherwise, I'll just carry on from 9.3, I think. Yeah.
Okay.
Yeah.
So, sorry, I just did it here.
Okay.
If you want me to show you.
Yeah, that'd be great.
Okay, I just did this share screen.
Yeah.
Yeah.
Let me stop sharing here 1 second. Okay. Okay, so there we go. Do you see the window magnification? I increase it. Okay, so this is
good.
the Frechet distribution. You do the limit 1 minus e to the this over x minus alpha. When x goes to infinity, it gets 1.
Yeah.
So you know that that quantity goes to x minus alpha. Yeah, it is counterintuitive, but it's something that some of our visitors here will be able to tell us, like Mr. Menon, for example. Okay. Okay. All right. So let me stop sharing.
Right.
Okay. Great. All right. Thanks for that. Yeah, I learned something there as well. Yeah, thank you. Okay, so we'll just go back to the, I think 9.1.3. Yeah, so this piece 9.1.3 is kind of changing from, I think, one of the extreme value theories to the second theory, and Fergal touched on this a little bit, that the two kind of link up through the value of the shape parameter. So the shape parameter of the Frechet distribution, which is modeling the maximums from a particular underlying distribution, I think that comes out to be the same shape parameter as in this GPD distribution, which can be used to model the tail. So this Pickland's Balkema-de Haan theorem is effectively the second part of extreme value theory, and it says that you can model the tail of any distribution above a certain threshold using the generalized Pareto distribution. So that's basically what that theory is. And I had, I think, a slide. Can you see those slides? Have they come up?
A chat. I see a browser.
I see. Okay. Sorry. Okay. Yeah. Right. Yeah. There you go. Okay.
Yeah.
Perfect. Okay. So yeah, just kind of visual presentation of this then is we're basically for this approach, the second approach to extreme value theory is you're kind of modeling just the tail. So you have your threshold, then you kind of model just the data in that tail, and that theory we just went through, Pickland's Balkema-de Haan theorem, is that you can do that with this generalized Pareto distribution as kind of a 2-parameter or a 3-parameter version. So what you do is you kind of put in a threshold, you ignore, let's say in this case example, I just showed 90% of the data is kind of dumped, and then you fit a generalized Pareto distribution to your data above that threshold, and then you can kind of use that to estimate a percentile or something using that kind of formula. But that's what I think section 9.1.3 is saying. Section 9.2. So yeah, let me go back to that actually, because I think this one's quite an important chapter, quite an important section, because it is kind of talking about this invisible tail for a parallel class. So it's I thought this was kind of like a mathematical specification for the black swan, effectively. So what's happening where you don't have any data. So you have your distribution, and you have your kind of historic data, and then beyond your highest point is this k in this plot, and you effectively have no information on what's beyond k, but there's obviously a lot going off there. And if you have these fat tail distributions, then you can really have a huge amount of your information is in that sort of place where you've got no data whatsoever, which is kind of a fundamental problem if you're trying to use that data to infer sort of what's the nature of some reality you're looking at. But there is it's a course online which I found pretty helpful. Let me just show that again. Here we are. So the slides, dive back to the slide. So yeah, there's a YouTube link. There was a mini course which I found pretty helpful. I think it's just talking about this probably in a slightly clearer way than I'm doing. Yeah, so I recommend having a look at that. But going back to the book, yeah, we've got this plot here on pages that's 168. It's kind of comparing the expectation of mean in the sort of invisible tail compared to the mean for the full distribution. So you have a kind of ratio there of how much of the mean is above where you've got any data compared to the full mean for the full data set. So this is quite worrying. So if your Pareto distribution is if it has a kind of quite a high parameter like 2, for example, relatively high in this plot, that's the bottom line. So that's saying the kind of unknown data is making up a kind of small proportion of your total mean. So if you have like 10,000 points, then this kind of unknown data is making up pretty much a negligible amount of your total mean. But if you have a shape parameter that's like 9/8, as in this case, it's making up a huge proportion. It's making up 50% if you have say 50, I presume that's around 50 data points. But even when you get up to 10,000, it's not getting much better than 40%. So if you have these very fat-tailed distributions, you find that the kind of hidden tail is making up a large proportion of, in this case, the mean, but presumably the other higher moments as well than the mean. And there's kind of another plot here showing similar information really for different sample sizes with 100 or 1,000 or 10,000. Yeah, so proposition 9.1 is giving this basically this formula, which I think is using these plots. So based on the number of data points you're using, the distribution of this hidden moment, mu kp, or we've got mu 1 here, which is the mean, but you can get higher orders as well. So there's a kind of distribution for that in that parameter, in that formula 9.12. And there's an expectation here of the pth moment above k. So there's a kind of a formula for that expectation, which I think is just the expectation of this up here. And I did do a small amount of algebra to kind of get that ratio we just saw. So the Pareto mean is just this value here. And if you just divide that by that, you can kind of come up with this formula for that ratio for a given Pareto distribution, which is defined by the scale and the shape parameter, and for a given k, you can kind of identify sort of how much of your mean is missing above that point. Which it's almost embarrassing that I've not really seen this before, because it seems like such a key point. It should be on kind of stats courses, I think, more commonly. Yeah, let's go on to the next section. So yeah, this just kind of a bit more discussion of this relating to the hidden tail for the normal distribution, proportion of the hidden mean in relation to the standard deviation for various values of n. So yeah, we have an equation here for the invisible tail for the normal, which isn't quite as serious an issue as it was for those fatter tail distributions. Section 9.3, there is a quote from this paper by William Gottsman, Dassel Kim, and Robert Schiller. So at least one very famous person there. And it seems to be saying that there's a sort of, I mean, I just had a look at the abstract, and my take on that was, it was sort of saying the fears of maybe market participants in this survey perhaps weren't merited by the historical data. And that was the kind of gist of the paper. So I had a brief comment on that in which I think comes down to that Lucretius fallacy that Fergal mentioned on the previous section. So this thing on the tallest mountain that you've seen being the worst event, as an example from Alex McNeil's 1998 paper in Risk Magazine, and it was using the method that Fergal described there. This sort of these extreme value distributions where you just fit to the maximum. So it compared like the Black Monday S&P 500 one-day fall, which was 20.4% on a single day. And if you're just taking that from the normal distribution, as I think people probably were at the time, it comes up as this sort of insane 1 in a trillion year event, or probably much more significant than that. But if you take that method that Fergal was talking through, and you fit use that sort of block maximum method, which I think is the first theory, EVT theory, to a set of daily returns from 1960 to 1987. And if you divide it into blocks of 1 year and you pick the maximum, the 28 maximum, the largest fall in the data set was just 6.8%. But then if you fit a generalized extreme value distribution, or the Fréchet distribution in this case, it gives like a 1 in 50 year event for a 24% fall, which is kind of in excess of what happened in 1987. So it shows that model is kind of far more plausible with what we see in reality than what was expected. And also maybe that I'm not quite sure I interpret it correctly, but that paper seems to say people were too worried, but perhaps the reality is they're maybe not worried enough.
So may I jump in? Just what happens is that a lot of these people tell you, well, people are overreacting to this random variable, not realizing that taking the minimum over a certain period of time is not indicative of the true minimum. You see, it's like you're saying, and that's why I use the this image of what's his name, the thing about the floods, the Lucretius idea that the widest river there is necessarily going to be wider than the widest river you have seen.
Yep.
You see the idea. So, and this is something that's not. And the reason I'm picking on these is because what's his name, Gutzman, all right, claimed that I write airport books. So just to give him a hard time, you see. Okay. So I mean, it's very easy for finance professors. They don't know anything you're doing, and they dismiss it. And that was in the Black Swan, by the way. All of this, but verbally.
Okay.
So this is why, I mean, you find flaw in their work to just, I mean, you find a flaw somewhere, but you single out those who are assholes. Okay.
Okay. Fair enough. Yep. Okay. Okay, so I think that's chapter 9. There were now some sections where sections B, C, and D, which are kind of applications of chapter 9. So sort of appendices. I think one of these, I think this perhaps wasn't in Fergal's book, but it was in mine. It's in the PDF. So maybe this got added in some point in 2020. So it was using this extreme value theory on the pandemics. And,
I got a hidden distribution of that book.
Yeah, it's the hidden distribution of our book. Yeah, exactly. So it was basically just talking through the pandemic and the shape parameter for the pandemic. I think there was some calibration of that, which were extremely low numbers. So we looked in that previous example on the previous page. So
this is not yet in a printed book.
I think it's in mine. It's in mine, which I got from the book depository, but it wasn't in some other versions, I think. So I don't know.
Okay. All right. It was not in a US printed one. Anyway.
Okay.
So.
Yeah. So the shape parameter here is really low, so 0.2, 0.25, and that is significantly lower than what you see anywhere else normally. So we looked at those examples above where there was a shape parameter of 2, and the lowest one was kind of 9/8, and that had a sort of a huge proportion of the mean is kind of beyond the tail of where your data is kind of invisible. So for these numbers here, it probably means just an enormous proportion of the information is not in the data, and it basically reached the conclusion here is that this is the lowest tail exponent ever seen by the authors, and I think the conclusion at the end of the chapter is you should just rely on precautionary principles and kind of act fast rather than later, which is something I kind of, to be honest, wish had been done in the UK with that last pandemic. Now, section Appendix C, large deviation principle. In brief, so this chapter I kind of struggle with a bit, to be honest, but the basic principle here is that a lot of these diversification ideas rely on the tail probabilities decaying exponentially. So as long as that happens, then you can get kind of your diversified portfolio and so on, as in Markovitch and so forth. But if not, then which is probably more likely to happen in practice, if not, then you won't get the same diversification. So that was, and there's a kind of a proof there as well for that result. Finally, the chapter D is about calibrating the Pareto distribution. So there's a couple of methods here described. So there's the maximum likelihood estimate. So the maximum likelihood estimate for calibrating a Pareto distribution, and I believe it's being compared to the method of moments example. And with the method of moments, you don't have all the information you need, so you're kind of missing some of the data, so you kind of misspecify your distribution, your calibration method. And there's a kind of example of that here with the true mean being way higher than the kind of sample mean in this data.
I think maximum likelihood, taking logs versus taking the sample average.
Exactly. So in other words, the difference between the two methods is, in one, you take the average, sample average. It doesn't work. But if you calibrate the alpha happens to be inverse gamma. So it's sort of have a sort of a Gaussian attributes to it. You see?
Okay.
So instead of looking at the mean directly, you derive the alpha and then get the mean, you do a lot better.
Yeah. Okay. Yeah. So you derive the alpha.
So in other words, instead of looking at counting the mean every time, okay, because the mean, if it's Pareto, the mean also would be Pareto. But if the distribution is Pareto, the alpha error on the alpha calibration is not Pareto. So in other words, if I generate random numbers, okay, and ask you find the mean, you're going to have a distribution for the mean according to that kappa that will converge very slowly. But if every time you have your run, you take the alpha converges faster.
Yeah. Okay. So
Okay.
so you
And then you got the mean for Pareto. The mean is L alpha over alpha minus 1.
yeah.
So does that
Okay, so
mean,
Sorry?
would that mean anytime you're working with financial data, you should try and do some like indirect method to get the
Exactly.
So you calibrate the alpha using the maximum likelihood, then you use that to calibrate the mean. Yeah.
Exactly. It's easier, or you have a cleaner view of the mean.
Okay.
Because the alpha gives you extrapolates over the thing you haven't seen. Whereas the mean does not extrapolate. The mean is an in-sample proposition where the alpha extrapolates out of sample.
Yeah.
Does it matter what method you use, or is the main thing to do is just start with alpha?
The alpha has a better handle of the unseen observations.
Or like when you're estimating the alpha, does it matter how you do it?
No, there's something called the Hill estimator that I used here. The difference is, for the Hill estimator, the alpha is Gaussian, is inverse gamma.
Yeah.
Or you can do regression, or you eyeball the alpha. The best way is eyeball the alpha. If you have good eyes, if you own a computer, have good eyes, and like colors, you can eyeball the alpha.
Okay.
And then start fitting, oh, that fits.
Yeah. Okay. Yeah. So I put that table, which was a list of references where people have calibrated alpha, and it was for all different. It seemed to be mainly engineering and hydrology and sort of practical type topics.
Great work. By the way, both of you, sorry, I didn't make compliment to Fergal. Marcos, I never give him compliments. He doesn't need it, but Fergal and then now. This is great work. Thanks. Sorry, guys.
Okay, wonderful. Okay, thanks. So this last slide just showing a load of papers of all different calibrations of the Pareto, which is in that paper. They're kind of linked there. But I think that's the end of the section. So that was the end of section D. So if there are any questions, yeah, please. Oh, there's one. Okay, there's one question there. Is there some heuristic for eyeballing alpha, or does it come from experience?
You're asking me?
I am. Yep. Yes.
No. I'm given that I have my beard is turning from gray to white. I can tell you that it's not 99% experience. It's 100% experience.
Would you eyeball it by saying like it's within these bands, and then
Yeah, exactly. You have an idea of the alpha by experience. Instead of doing this, you put the plot, log plot, and then you fit the alpha. You fit a lot of, see which one maps the most to what you're comfortable with. Because you see at the end of the data, towards the tail, it's going to fall off a little because of insufficient sample. Visibly, you don't have a lot of sample in the tail, so the alpha is going to fall off. So the idea is just do it by eyeballing. Some other time now, I mean, I guess I don't want to take more time. Some other time, maybe I'll drop by and calibrate an alpha live. We take something like Bitcoin if it's still around. If it's not around, we'll find something else and then calibrate the alpha.
Well, you have that tallest mountain slide. A good question to ask people is like, what was the tallest mountain in the world before Mount Everest was discovered? And a lot of people will say K2. But don't ask a geography teacher. They'll feel bad.
Okay, so if there are any more questions on chapter 8 or chapter 9, otherwise, I'd say thanks very much to the speakers, to Marcos, Fergal, and Nassim. Thank you very much for attending.
Thanks a lot. Thank you I'm so honored to have everyone here, and have a great day.
Yeah, perfect, nice one. I'll be back next month to do chapter 10 and 11. If there's any volunteers to talk through one of the chapters, yeah, please get in contact on Twitter or via the website. Okay,
Great.
thanks everybody.
Thanks a
Thanks,
lot.
everyone.
Thanks, everyone. Thanks. Bye now.
Bye.